Okay, on the bench here we have a big mess of parts, and what this is going to be is a 25 watt per channel amplifier. This was a very inexpensive kit that I purchased online, and here's a little schematic of it. It's not a very good schematic, but nevertheless it's what we got. And I think somewhere here I should have something showing right here what it is. Oh, they're calling it a 100 watt. That's kind of, I think that's a little bit of a stretch to call it a 100 watt amplifier. And you could see the whole kit cost a whopping $7.90 American and $1.97 shipping. And I have to admit, I was really surprised how quickly it came in. It came in with with only a week or maybe 2 weeks at the most. And as you can see, if you buy 4 or more of them, they even give you a 15% discount. So what the heck, you know? The only thing you need to provide is a power transformer, and I'm pretty sure I have one of those laying around. I think they want I think it's plus and minus 15 volts or something, or what are they saying? Not sure. Let's go back to the schematic. I think it says, yeah, plus or minus 15 volts. So I think we have that for sure. So really, all we need to do is just kind of put this thing together. So I'm not going to bore you with all the details. You've seen me assemble kits before. I kind of question these little heat sinks, whether they're going to be adequate. Obviously, at plus and minus 15 volts, that's not going to give you a 100 watt amplifier. This is going to be closer to maybe 15 to 25 watts per channel. But it should be a pretty, these two N3055 transistors that they use in the outputs, these old TO3 jobs here, they're pretty substantial. So, you know, all things considered, I bet you this thing's going to actually sound pretty good when we're done. Let's see. It even has 105 degree capacitors. I don't know, we'll see. But let's try it out. Let's put it together, and I'll find a power transformer, and we'll just kind of throw it on the bench and turn it on and see what happens. How's that? Well, now, it's been, oh boy, close to a week, I would say, since I finished soldering this thing up, putting it together, and have not had a chance, because of work and other obligations, to really see how this thing turned out or if it's even going to work. So I have some free time, which I don't have much of with work lately. It's been so crazy. But I thought I'd just relax a little bit and come down here and continue our project and see what we've got. So as you can see, the whole board's been assembled and turned out pretty good. Now, a couple of notes here. First of all, I assembled this thing straight stock, the way it came to me when I ordered it. I'm using all the stock components. I'm using the stock heat sinks. Everything. I did not change any components in here. So what you see on this board is the way that this thing comes. So if you want to build one of these yourself, this is what you'll get. Now I have another one that I ordered. I ordered 2 kits from 2 different vendors, and I believe that this one is it is a bit different. If you see, it's got a little different layout, but circuit-wise, I believe it is a very similar circuit. I know the component values are all the same, just the board layout is a little bit different. So, and if I do verify that it's exactly the same circuit, when we build this second one, I'm going to make it a little sport to go ahead and try to modify it and see what we can do with this. But I want to see how this one works as it is. So as you can see, I have a little transformer, nothing special. It's a universal one and made by Triad. If you want to look at the part number here, you can order these online. You know, all the parts houses out there have them. Okay, see there's the part number. But this is just one I had. It was not something that I went out special and bought. So it's basically rated at 24 volts center tap. So it's plus, and it's basically 12 volts, 0, 12 volts. And it's wired that you can wire this one for 120 volt mains or 240 volt mains. So this will work here, and it'll also work over in Europe. So, if any of you want to build one of these, this is all you need. Technically, this is it. Here's your input, here's your speaker output, and here's your 3 wires from your transformer. Power supply, preamp, drivers, everything is all one board. Okay? And we'll take a look at it a little bit later here at the schematic. We'll see if we can call it up. But the first thing we want to see is, will this thing work, or is it going to let out the magic smoke? I don't know. What I've done is I just wired a plug to the end, into this transformer. I'm kind of going by the seat of my pants, but I have the dim bulb connected, and I am set to limit, if you look right there. And so what we're going to do is we're just going to plug this into the limit and just see if it turns on. If anything shorts seriously, the bulb should take it up. Now a safer way would be to very slowly bring it up on the variac and watch the current and do that, but hey, what fun is there in that? So here we go, we're plugging in. And there you go. If you look, we do have a light. Now I don't know what that means. It means that I guess the light works. But first of all, let's see what AC voltage is going in here. Now remember, I'm still going through the dim bulb. Okay, so 2 outer windings. We have about 28 volts AC. Center to one of the ends is 14 and 14. I thought this was 12 and 12. This is actually 15. This is supposed to be a 15 volt center tap. I'm sorry, guys. This is I forgot. This is a 30 volt center tap transformer. And under load, I have that, I have the bulb in there, so it's a little bit low, but plus and minus, or 15-0-15 is what it is, not 12-0-12. So disregard that first statement. Okay, so we do have our AC going in. So now we'll move the meter to DC. And this is your ground. And one side of these diodes should be your positive voltage, and you can see, or your negative. There's negative 18.8. Okay. And the other side should be your positive then. So positive 18.8. Okay. So we have our plus and minus 18 volts. Okay. And again, this thing will run up to 18 volts AC in, which would give you 24 volts DC, something like that. 1.414 times the, the formula. But if you put a bigger transformer and put a little higher voltage on this, you will get a little more power output from the amp. I don't know what the distortion will do. We're going to test all that. And I'm sure that will increase the heat of the transistors, which right now are running, literally freezing ice cold. So my next thing I want to do is I'm going to take a signal out of my signal generator and feed it into these 2 input pins and connect this up to our dummy load and see what we get. So give me a second to rig that all up, and I'll be right back. Okay, as you can see, I have the amplifier all put together, and I did find one problem. I tried to do this thing bone stock. In other words, I did not make any modifications to it. We're going to test this thing out just as it is, just the way that it was built, or that it came as a kit. So in order to do that, I just soldered everything together, but I did find one problem that I did have to do, and I did have to change some components, and that was right here. Alright, so if you take a look, these little capacitors, and you can see how tiny they are, they say 103, which would kind of indicate to me a 1, a 0, and 3 zeros picofarads, right? So that would be 10,000 picofarads, correct? And when I read them, they both read differently, and neither one of them reads anywhere near that. And to make matters worse, when you look at the schematic here, these capacitors here are calling for basically I think they're saying 1,000 picofarads, right? Or 101, 100 picofarads, I'm sorry. 1, 0, and one more 0, which would be 100 picofarads. So what I did was I went ahead and put a couple of 100 picofarad capacitors in there. All the other components tested out good, and kind of agreed with the schematics and everything. Another thing I noticed is on the silk screen of the board, they're calling for 18 volts AC from line to center tap. So they want 18, 0, 18. If you look at the schematic, it says 15, 0, 15, and they're calling for 18 volts DC after rectification. So looking at the component values, if I put 18 and 18, this is going to make the output voltage relatively high. These are 35 volt rated capacitors, and if you take that 18 volts AC and you go 18 times 1.414, that's going to give you about 25.5 volts on a 35 volt rated capacitor. So you're going to be running those really pretty hot. The other thing is these tiny little transistors, I really don't know what their maximum voltage is rating. So I'm a little bit nervous about that. So I do have an 18 volt 18018 transformer over here, as you can see, and this one here is a 12012. If you want to take a look at what I have there, I'll show you the part number right there. Okay, and right there's the part number. And what I've done was I've connected it up to my variable power supply, you know, the variac, and I just dialed it in until I got an actual plus and minus 18 volts DC into here, which is giving me roughly 15 volts AC coming in. Alright, following me so far? Now, the design of this amplifier is a little bit unique. I actually had to do a little research because I've seen these in old console stereos and things before, this type of weird design. Because you see kind of a Darlington thing going on right here. And if you notice, this is a push-pull amplifier. Here's where your speaker connects. Here's where your speaker connects. But if you notice, these are both NPN transistors. Now, normally, in a push-pull amplifier, you would see what's called a complementary symmetry amplifier. And you would see a NPN on one side and a PNP on this side. Okay, and they would be driven by a differential power rail, so you'd have a positive voltage here and a negative voltage here. Well, you still have the positive voltage here and the negative voltage here, but you have two of the same polarization of transistors. And what we call this design is called a quasi, or quasi, Q-U-S-I, quasi-complementary symmetry amplifier. So in other words, it's not true complementary symmetry, but it is kind of a variant of that. And don't ask me all the theory behind this, because I don't quite understand it all myself totally, but I do understand that you basically have these little Darlington kind of connected almost in Darlington. You see this one, you have the output, the collectors are tied together between this driver and this output. The emitter of the driver goes directly into the collector, so it's direct coupled to the output. And down here you have a similar situation. You actually have the collector of this PNP direct coupled into the base of this output transistor. Okay, and then you have you basically have a voltage divider here, 220 ohms, 240 ohms. So this is not quite a Darlington here, and there is a name for that, and I forget the name of it. It's a funny name I can't describe. But basically, that is how they are getting the phase splitting. And this circuit here is critical, because here is your pre-driver to all of this mess. This one up here, this VT3 or VT10, depending which channel you're talking about. And how this works is what controls the actual bias of this output circuit. And I would kind of imagine you'd want one of these resistors, I think this one up here, you would want that to be a variable so that you could adjust the bias to be able to not get any kind of crossover distortion. Because if these are both turned off fully at the same time at any time, that little delay from when one kind of quits conducting and the other starts conducting would give you a crossover distortion. So I have the signal generator connected up here, and I did do a quick little test run of this, and I did connect it up to the oscilloscope. And what I'm going to do now is I'm going to go to a split camera mode, and we're going to turn this on and put a signal onto it. Now that you know kind of the scenario, this is coming from the signal generator right here. I'm going to just do your typical 1 kilohertz, okay, into each channel, and I'm going out into my resistor dummy load over here, and we all know that from our previous videos. And we're going up to our oscilloscope, and we're going to kind of look at the waveform. Now, what I found is, number one, this thing is really sensitive, because I kind of wanted to get this a little set up before I, turn this on for you guys. And one thing I noticed is this amp has way more gain than I think it needs. I found at about 50 millivolts going into the input terminals, I'm getting basically full power output, which isn't a whole lot, by the way. With 18 volt DC rail here, plus and minus, I'm lucky to get about 8 volts of clean power, okay? And that's really all I am. All I'm at right now. I stopped right there, and that's where we're picking up on this video. So now that the scene has been set, let me get the cameras set up for the next shot, and I'll show you what everything looks like. Okay, hopefully both cameras are running here. You can see on here we have the scope set up for our 2 right and left channels, and I have my signal generator ready to turn on, and we're going to go ahead and fire this up and see what kind of output we get. So first things first, kick the power, and I just want to make sure that I have the proper voltage here. So we're going to get the voltmeter into the scene here, and I'm just going to look at the negative side, and I have negative 20, so it's a little bit hot right now, and positive 20, and that's going to be a little bit hot until I start loading this down. That's the other thing about this circuit is it kind of doesn't really draw much current at idle. And because it doesn't, the power supply rail can drift up a little bit because there's no load on the transformer. Now, as we start to load it down, we're going to notice that that voltage will probably drop a little bit. So here we go. And you can see right now I have a pretty nice sine wave, but take a look here. If you notice, there's some little tick marks here, here and here, here and here. And what that is that's what we call crossover distortion. That's again where that signal starts swinging from the positive part of the cycle to the negative part of the cycle. You can see that little transition point is where you're actually seeing there's a little tiny delay there, and that is causing that little moment of 0 volts, which is giving you crossover distortion. Now, you may not hear that, I don't know, in the real world, but again, I'm not sure. But that could possibly be because this does not have an adjustable bias like we were talking about. If we look up here at the measurement, we're getting 6.464 volts. Okay, so if we take 6.464 times 6.464 and we divide that by our 8 ohm load, we're only getting about 5 watts, 5.25 watts, okay? And that is with 50 millivolts going into it, okay, of RMS at 1 kilohertz sine wave. And you can see just going up, well, there we go, I got a little bit more out of it, 60 millivolts. And you can see at 60 millivolts, that extra 10 millivolts drove that up, that output up pretty substantially till we're now at 7.684. Okay, so see how sensitive the input on this is. So 7.684 times 7.684 equals, divided by 8. Now we got about 7 watts, 7.3 watts. And really, with a DC rail of plus and minus 18 volts, I wouldn't expect a whole lot more of clean power than that. The other problem is we're talking about a, little 1,000 microfarad capacitors, 2 of them in parallel, so that's actually 2,000 microfarads. And if we look at our voltage now under load, we're even a little bit under 18 volts now, 17.7. So you can see how the power supply drifts as you put load onto it. And again, it's just a function of the design of this amplifier. So yes, this was a cheap $7 kit, and I assembled it as it came, as I received it. I didn't do any modifications. Okay, and pretty much we have a pretty clean, with a little bit of crossover distortion, not much, you can see it up there, right? A pretty clean sine wave at about 7.2, 7.3 watts per channel. That's all we're getting. Okay, so let's shut this off now and let's regroup a little bit and take a look at maybe what we can do to make it a little better, if we can. Okay, so we're looking at the schematic now, and once again, really what I saw wasn't terrible, but it also wasn't great. Okay, so what can we do to make it better? Well, the first thing we can try to do, we can't really do a lot with the power, because in order to get more swing out of this, you would have to increase the rails, okay? And in order to do that, you would have to choose components that can handle the higher voltage, okay? Which I don't know about these little Chinese transistors, what they're capable of handling voltage-wise. And even if they could handle the voltage, we would need to probably change some of these resistor values so that we don't exceed the current either by increasing the voltage. And then we would have to give you an appreciable change in the voltage swing, in the gain and everything to get that power. It's not easy, is what I'm trying to say. What we can do is try to minimize the distortion so that if we drive this a little harder, we can get closer. I bet we could probably get between 10 and 15 watts per channel out of this amp if we got it to stay clean all the way through. Part of the problem right now is the signal's distorting when we get too much above that 7.5 watts per channel. So first thing I'm going to do here is I think we should take this R7 and R18 and we should probably go and put a different resistor in here, like a pot, so that we can adjust it. So like maybe put a 1K potentiometer, and so it would look something. Let me move some of these things out of our way. So we would have something that looks a little bit like this, where we would take R7 and we would take a wiper and just kind of go up to here, tie that together, and then make this a 1K. And if we did that, we might be able to shift the voltage on this a little bit to change the bias a little bit to get that crossover distortion to go away and to kind of change the swing of, in between these. So that's the first thing we can do. Beyond that, these are not very big capacitors. Now, one thing they did do was, instead of putting a 2200 microfarad on each rail, they put two 1000 microfarads, which add together. So you have 2000 microfarads, but because those two capacitors are in parallel, they also reduce the ESR, the equivalent series resistance, which that's a good thing. But that being said, I would rather see closer to, a 3300 or 4700 microfarad capacitor, because you're driving two channels. So you really kind of need a little bit more reserve, especially when you start going to the low frequencies and so forth. The other thing is these little 10 microfarad capacitor inputs, they're probably not audio grade. I would doubt. They're very low cost. I mean, the whole amplifier, remember, with the heat sinks, the output transistors, all the components in the board, only cost me a little over $7. And you can find these all over the place online, okay? So, on eBay, and Banggood sells them, I think, and you could probably find them on Amazon. Lots of places sell these little kits. And my goal really never was, they call it a 100-watt amplifier. My goal never was to see that kind of power out of this. You're never going to. That's not realistic. The voltage, the math won't allow that, with this plus and minus. You would have to have a lot higher rail voltage. Could we push these voltages up a little bit? Yeah, I doubt that it's going to change the power, though. So the goal here is a little bit better capacitors here. Put in a potentiometer to see if we can reduce or eliminate the crossover distortion. And if we get any, I see a wee little bit of parasitic oscillation still when you start really cranking up on it on one of the cycles. So maybe play around with this 100 picofarad capacitor, maybe go up a little or down a little to tweak that a little bit. So between those couple of things, maybe we can make this a little bit better circuit. So that's what we're going to do, and then we'll come back and see what kind of improvement we've made. What we did here was we ended up switching out this resistor right here, which on the schematic is right here that I was talking about. It went from a 220 ohm to a 470 ohm. And what I want you to do now, I'm going to flip the power on. This bottom one is the one we've modified. This is the original. And if you look, as you can see, there are absolutely no crossover distortion lines here. But if you look at this one that's not modified, you can still see them very clearly. So it looks like 470 ohms is where we need to be with this. So I'll get those fitted in there, and then we'll give this thing another test. Okay, we got this thing wired up to a set of speakers, just a little set of Radio Shack Minimus 7s, my little bench speakers, and I'm gonna just play a couple seconds because obviously I don't want to get busted with the music police here, but I'll give you a quick sound. This thing's really sounds good. So here we go. Let's see here. Pretty good, huh? Has really nice tight bass to it. These are running ice cold now. Those 470 ohm resistors and those 200 picofarad capacitors seems to be all it needed. And actually, I gotta say, I gotta give this amp a thumbs up, guys. For a $7 thing, you might have to change a couple resistors and a couple capacitors, but good grief, you know. And it gets really loud too. So I think this is going to be one of my bench test amp. I'm going to build one of these for that. Now maybe next we'll do another video where we'll actually test out how this, you know, what we can do with this thing if we modified it. You know, put better power supply and better quality components and maybe juice it up a little bit. I bet this will be a really good amp, and I bet we could do it for under 25 bucks. Now, of course, you still have to purchase a transformer, which, of course, the transformer's a little bit, you know, costs a little bit of money, but unless you have one. But the amp itself, man, how can you go wrong for that price? So I think we'll end this video here, and I hope you enjoyed it, and I hope you learned a few things, and lots more to come. Remember, as always, thumbs up if we did a good job, and thanks for watching.